Write down the meaning of the term reversible reaction. So, a reversible reaction is a reaction where the products can be turned back into reactants. That is the answer to 6.1. 6.2 state Le Chatelier's principle. Okay, this is very key to chemical equilibrium. Chemical equilibrium is basically based on Le Chatelier's principle. Well, it says that when equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring a reaction that opposes the change. That is Le Chatelier's principle. Let's take a look at 6.3 and 6.3.1. A change was made to the equilibrium mixture at t is equals to 80 seconds. 6.3.1, write down the change made at t is equals to 80 seconds. So let's go ahead and have a look. This is t is equals to 80 seconds. We have a reaction to AB giving us and getting A2 plus B2, right? At t is equals to 80 seconds, you can see clearly that the concentration, not the concentration, but the number of moles. The number of moles of A2 are increased. There's an increase in the number of moles of A2. And then as a consequence, when the system wants to reinstate a new equilibrium, the reaction that reduces the number of A2 is going to be favored, which is the reverse reaction. That is why we see the number of moles of B2 decreasing and the number of moles of AB increasing. So the answer to 6.3.1, number of moles of A2 are increased. Okay, so the number of moles of A2 increase. That is the change that is made at t is equals to 80. 6.3.2, use Le Chatelier's principle to explain how the system reacts to this change. Okay, I think I've touched on that, but let's just go through it again. So let's take a look at our reaction. If you increase the number of moles of A2, the system will want to reinstate a new equilibrium by favoring the reaction that reduces the number of moles of A2. Clearly, the reverse reaction reduces the number of moles of A2 because A2 plus B2 will be turned to AB. So that is how the system will react to this change. It will reinstate a new equilibrium by favoring the reverse reaction that leads to less number of moles of A2. 6.3.2. 6.4. Let's take a look at 6.4. So in 6.4, calculate the equilibrium constant Kc at t is equals to 120 seconds. And then the allocation is 4 marks, right? Yeah, this is a nice question. Unlike the questions we usually have where you have 8 marks, 9 marks, so on and so on. So to find the Kc, we need to say that the concentration of the products, so we have A2 and B2, divided by the concentration of the reactants. We have AB. We have to take the concentration of AB to the power 2. We are doing that because of this balancing coefficient. Okay, so Kc will be equals to, we're interested in T is equals to 120. T is equals to 120. We have the number of moles of AB, the number of moles of A, and the number of moles of B2. And we are given the volume in our question statement. It is said to be 4 decimeter cube. Okay, so let's go ahead and find the number of moles, not the number of moles, but the concentration of A2. How many number of moles do we have? We have 8 number of moles for A2. We have 8 moles, right? So we're going to have 8 divided by 4. Number of moles divided by volume will give you the concentration. Multiplied by the concentration of B2. How many moles do we have? We have 2 moles. So that is going to be 2 divided by 4. Everything divided by the concentration of AB. We have 10 moles of AB when the temperature is 120 degrees. So that's going to be 10 divided by 4 to the power 2 because of the balancing coefficients. So now it's just a matter of putting that in my calculator. So let me go ahead and do that fairly quick. Divided by 10 divided by 4, everything to the power 2. I have 0.16. So there we go. That is our Kc at t is equals to 120 seconds. Okay, 6.5. At t is equals to 130 seconds, the temperature of the system is decreased to 100 degrees Celsius. Okay, and then 6.5.1, let's draw a potential energy diagram for this reaction. Okay, let's make sense of the situation we have. Let's go to our graph and look at T is equals to 130 degrees, because that is where the temperature is decreased, and see how our reaction is reacting to that change. We have 2AB to give and to get A2 plus B2. Let's go to T is equals to 130 degrees. Let me just erase all this for the sake of clarity and draw a line at T is equals to 130 degrees. Okay, at T is equals to 130 degrees. Let's take a look at the amount of AB. The amount of AB increases. The amount of A2 decreases. Same is true with regards to the amount of B2. So our reactants, the amount of reactants we have decreases, while the amount of products increases. Okay, so let's make sense of that. Temperature was decreased and the reverse reaction was favored. If the number of moles of A2 and B2 are decreasing, it means that that reaction was favored. A2 and B2 were converted to AB. So decrease in temperature, let's make sense of that. So when the temperature was decreased, reverse reaction was favored. Which reaction is favored by decrease in temperature? That is exothermic. So the reverse reaction is exothermic because it was favored by decrease in temperature, which tells us that the forward reaction is endothermic. Okay, right. So now we need to draw a potential energy diagram for a endothermic reaction, for a reaction where the forward reaction is endothermic. So what are we going to have? Let me show you. We have our y-axis and we have our x-axis. So cost of reaction and potential energy in kilojoules per mole, usually. Okay, so if we're saying that forward is endothermic, then we're going to have something that looks like this. We have our products A2 plus B2. We have our reactant AB. Okay, I think that is all we need. We can obviously show that this is our activated complex. Let me show clearly that the energy of the products is greater than that of the reactants. Let me show that, okay? So that when I show my enthalpy, it's easy to see, right? So this is my enthalpy. Energy of products minus energy of reactants. 6.5.2, will the equilibrium constant Kc at 100 degrees Celsius be greater than, less than, or equal to the Kc at 150 degrees Celsius? Explain the answer. Okay, it will be less than. It will be less than. Okay, let's explain why it will be less than. It will be less than because when the temperature is decreased at 100 degrees Celsius, we're going to have less product compared to at 150. Because if you increase the temperature from 100 to 150, your forward reaction is going to be favored. You're going to have more products versus the reactants. So 6.5.2, we have less than. And the reason I just gave you right now. Forward reaction is endothermic. So if you decrease the temperature, reverse reaction is going to be favored. We have less product, so the value of Kc goes down. Okay, because Kc is products divided by reactants. That is why we are seeing less than. 6.6. Let's take a look at this one. The initial reaction now takes place in the presence of a catalyst at 150 degrees Celsius. Describe the changes that will be observed on the graph between t is equals to 0 and t is equals to 60. So let me know in the comments, how did you answer 6.6? What I'm currently thinking is that if we add a catalyst, then we will provide an alternative path of lower activation energy. So both the forward and the reverse are going to be favored, right? The rate of reaction is going to be increased. So we are gonna reach equilibrium quicker, right? Before t is equals to 40, if we are reaching equilibrium at t is equals to 40. I wonder how you phrased 6.6. So just leave a comment and let me know how you answer the question.